So, galaxy collisions in the universe are reasonably common occurrences. These galaxy collisions take place, as I said, over hundreds of millions, billions of years for the collision to go through and complete. Right now, our galaxy is colliding with a very small galaxy. That small galaxy has collided with us. Our galaxy is tearing it apart, gobbling it up, and it is being absorbed as part of our own galaxy. Now, when that this collision I'm speaking of, our Milky Way colliding with the Sagittarius dwarf galaxy, that's not really going to change our galaxy much because our galaxy is just so much bigger than that other one. But when our galaxy collides with the Andromeda Galaxy is bigger than our own, so it is going to drastically affect what the final outcome of both galaxies is going to look like, turning them into a really large elliptical galaxy. Now, galaxy clusters then will gravitationally combine to form superclusters. So, our local group is a small group of galaxies in a supercluster Laniakea. Um, I say this with a smirk that sometimes, depending on where you look, the local group will be considered part of the Virgo supercluster, but the Virgo supercluster is also considered part of the Laniakea supercluster. Now, on the largest scales, there are more superclusters. So outside of this, there is the Sculptor supercluster, the Phoenix supercluster, Ursa Major supercluster. Most of these names of superclusters come from the constellation in that direction of that supercluster. Now, between galaxies is a diffuse medium of gas and dust known as the intergalactic medium. So, between galaxies, space is not truly empty. You just have a really thin, for lack of a better term, I'll say a really thin gaseous medium that you're passing through. And even between galaxy clusters, you have voids. These voids are not actually perfectly empty. Voids contain about 10% as much material as non void intergalactic medium. So, how do we really define what is a supercluster versus not? How do we define the boundary of a supercluster? So, why should we be considered part of Laniakea rather than Virgo? Where do we draw the border? And what we will see is the boundary between a supercluster depends on the direction in which material is flowing. Oop. There we are.
Somewhere in the universe is a small blue planet,
I know where
the
that is.
third rock from a star called the Sun, just one of billions of stars in a spiral galaxy known as the Milky Way. But where in the universe is the Milky Way? A team of scientists gathered data on more than 8,000 of the galaxies that surround us. They mapped each galaxy's position and movement in space. And, for the first time, they've shown that the Milky Way is part of a much larger system of galaxies, a supercluster that they have named Laniakea. The Milky Way is nested in the furthest reaches of this structure, on the outskirts. The entire universe can be seen as an intricate network of galaxies, a cosmic web. Some areas are almost empty, dark voids. Others are densely packed with galaxies in regions known as superclusters. Superclusters are the biggest structures found in the universe, but scientists have struggled to define where one ends and another begins. To map our home supercluster, a team led by Brent Tully at the University of Hawaii studied the motions of the galaxies around us in unprecedented detail. Even though the entire universe is expanding rapidly, gravity is also at work, pulling against this acceleration. By discounting cosmic expansion, the team worked out which galaxies are being pulled towards us, shown in blue, and which are being pulled away, shown in red. This enabled them to create a map of cosmic flows, the paths that galaxies migrate along, tugged at a tiny pace by the force of gravity. Using this motion, they came up with a new way to map the distribution of matter in the universe. Delving into our home supercluster, you can see that most galaxies are being pulled towards a dense center. This is known as the Great Attractor. Our galaxy is among those sliding towards this patch of space, which dominates our region of the universe. Let's take a different view. Each circle represents a galaxy. Again, we can see most galaxies being pulled towards the Great Attractor in the direction of the arrows. Between the Great Attractor and us, the Milky Way, there's a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light-years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is merely an appendage of a much larger supercluster, more than 100 times bigger and more massive. But how did the team know how to redraw the boundaries of this cosmic map? Here's our supercluster in black and a neighboring structure, Perseus Pisces, in red. The scientists defined the boundary as the points where the flows of galaxies diverge, like water dividing at a watershed. This is where neighboring structures shear apart. This is the first clear definition of a supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for the vast community of galaxies that we are a part of. So now we know that on the edge of a supercluster called Laniakea, in a galaxy called the Milky Way, around a star we call the Sun, there is a small blue planet, our home.
So basically what this video said is, if you are a galaxy, let's say you're right here in the yellow region, your galaxy is going to tend to flow along this line here and is being attracted towards a region somewhere around here. I'm not positive, I'm just making this up based on what the picture looks like. But if your galaxy is over here, you're going to be pulled this way. So if you think of a map, a 3D map of some terrain where you have mountains and valleys, you could say, and then you have rain falling on that terrain. All the rain that falls in one region will tend to flow towards one lake. All the rain that falls in a different part of the region will flow towards another lake. And where all the rain falls, if it all flows to the same place, that is one cluster. Where all the rain falls in a different location, if it all tends to flow towards a different lake, that would be a different cluster. So this is the first good robust definition of what is a galaxy supercluster. This definition was not really, this discovery of Laniakea, this definition of a supercluster, didn't really exist until fairly recently, 2013 or 2014. Go on. So on the largest scales, the universe ends up looking something like this, where we have filamentary structure. So we have filaments and what's known as a cosmic web due to the resemblance to cobwebs. So we have filaments of galaxies drawn in yellow. We have dark matter in purple, and then voids are in black where there is very little material. And if we zoom out even further, this map really looks like a cobweb. Now, this is just a simulation of what we think the universe looks like. And again, you write some computer software, you put a lot of particles in a box. The particles in the box are attracted to each other. It is actually a very... It's simple to explain, but it's a very complicated calculation to perform. And when that occurs, you just let the box evolve and see what it looks like. And does this resemble what we observe when we take surveys of the location of galaxies in space? Well, to a very good degree, yes, it is. So this is an actual galaxy survey. And we see that we are located right here near the center. And around here, we could definitely see that cobweb-like structure of filaments and voids that are fairly empty. Now, don't worry so much about how it gets more dilute out here further away from us. Part of that is due to the fact that you're looking really far away, so it's hard to see material. Also, when you look out far away, you're looking into the past. So if galaxies tend to get closer and closer together and become more clumpy as time evolves because of gravitational attraction, you would expect some evolution in that as well. But the take home message is what we observe in simulation is very close to what we observe when we conduct galaxy surveys. So that suggests that we're on the right track. So I'm going to stop here and I will continue with 2 more ways of measuring distances in the next video.